Welcome to Lightbox Radiology Education. MRI was discovered in 1947, simultaneously by two physicists, Felix Bloch and Edward Purcell. The first clinical images were obtained in 1977. MRI uses magnetic fields and radio frequencies, rather than ionizing radiation used in X-ray and CT. The magnetic field strength of an MRI machine is measured in Tesla. The majority of MRI systems in clinical practice are 1.5 or 3 Tesla, referred to as 1.5 or 3T. These produce an extremely strong magnetic field, up to 50,000 times that of the Earth's magnetic field. An electromagnet of similar strength would be able to pick up a car. The body is made up of 70% water, which is composed of hydrogen and oxygen atoms. MRI relies on the magnetic properties of hydrogen atoms to produce images. The hydrogen nucleus is composed of a single proton with no neutrons. As a spinning charged particle, this produces a magnetic field called a magnetic moment. Normally, the protons are orientated randomly, so there is no overall magnetic field. The components of the MRI system include the primary magnet, gradient magnets, radio frequency coils, and the computer system. MRI differs from imaging such as plain film radiography and CT scanning, as it uses magnetic fields and radio frequencies rather than ionizing radiation. The primary magnetic field refers to the strength of the static permanent field, for example at 1.5 or 3T. Hydrogen atoms align parallel or antiparallel to the primary field B0. This is called longitudinal magnetization in the long axis of the magnetic field. A greater proportion of the hydrogen protons align in the direction parallel to the primary magnetic field or low energy state than align antiparallel to the primary magnetic field, the high energy state. The net result, called the net magnetic vector, is therefore in the direction of the primary magnetic field. This is orientated in the patient's long or z-axis. The protons spin on their axes much like a spinning top. This is called precession. The precession rate is called the Larmor frequency. When protons precess together, this is known as in phase. When protons precess separately, this is known as out of phase. The frequency changes in proportion to the magnetic field. At 1.5 Tesla, this is 63.9 MHz. The gradient coils generate secondary magnetic fields over the primary field. They are located within the bore of the primary magnet. They are arranged in opposition to each other to produce positive and negative poles. The arrangement of these gradient coils gives MRI the capacity to image directionally along the Z, X, and Y axis. There are 3 gradient coils, which are named according to the axis along which they act. Gradient magnets alter the strength of the primary magnetic field, thereby changing the precession frequencies between slices. This can then be used for slice selection and localization in the X, Y, and Z axes, called spatial encoding, of MR images. The Z gradient runs along the long axis to produce axial images. The Y gradient runs along the vertical axis to produce coronal images, and the X gradient runs along the horizontal axis to produce sagittal images. The radio frequency or RF coils are used for transmitting the radio frequency or RF pulse and receiving signals in MRI. They come in many designs altered to best suit each body part, all aiming to improve signal-to-noise ratios to produce the best possible diagnostic images. The RF coil is used to transmit a second magnetic field or RF pulse, which results in a disturbance of the proton alignment. Some low-energy parallel protons flip to a high-energy state, decreasing longitudinal magnetization. Secondly, protons become synchronized and precess in phase. As a result, the net magnetization vector turns towards the transverse plane, that is, at right angles to the primary magnetic field. This is known as transverse magnetization. The radio frequency or RF coil is used to receive signals to create images, as protons resume their normal state in the primary magnetic field prior to transmission of the RF pulse. This is called relaxation. Relaxation in the longitudinal axis is T1 relaxation. Relaxation in the transverse axis is T2 relaxation. After the RF pulse, several protons flip back to their low-energy state, parallel to the magnetic field z-axis, giving up their energy to the surroundings, the lattice. This results in changes to the longitudinal relaxation, known as T1 relaxation or spin lattice relaxation. On a plot of magnetization over time, magnetization increases with time. This is the T1 curve. The T1 relaxation time will vary depending on tissue composition and structure. For example, water molecules move rapidly and do not move into the lower energy state quickly, so T1 relaxation takes longer. After the RF pulse, protons that were in phase begin to dephase in the transverse XY axis. This is known as spin-spin relaxation. This results in a reduction in transverse magnetization. Plotting transverse magnetization in the XY plane versus time, transverse magnetization decreases over time. In reality, the spins dephase much quicker than T2 because of inhomogeneity in the magnetic field B0. The combination of T2 relaxation and field inhomogeneity is termed T2 star. T2 relaxation times vary between tissues. For example, water molecules move quickly and as a result there is less field inhomogeneity. Therefore, T2 relaxation takes longer. The net magnetic vector is the sum of longitudinal and transverse magnetization. The net magnetic vector spirals around the z-axis with net precession. The changing magnetic moment of the net magnetic vector results in free induction decay. This induces an electrical signal. The signal received by the RF coil is in the transverse plane and reduces as the net magnetic vector moves to the long or z-axis. The computer system receives the RF signal and performs an analog to digital conversion. The digital signal representing the imaged body part is stored in the temporary image space, or K-space. The K-space stores digitized MR signals during data acquisition. The digital signal is then sent to an image processor where a mathematical formula called Fourier transformation is applied and the image of the MRI scan is displayed on a monitor.